present some concepts on Raman spectroscopy. So this lecture consists of two parts. In first part, I'm going to introduce the basic concepts, and in the second part, I'm going to speak about the instrumentation. And also, yes, there is a third part which will talk about some special techniques related to Raman spectroscopy. So I'm a scientist at National Chemical Laboratory, Pune. I am a physicist by training, and my email addresses are given if in case you would like to contact me. So I would like to suggest the following books. My favorite is Ferraro, and there are other books as well. For example, this book by Richard. And if you would like, if you want to learn about basics of light scattering from small particles, my all-time favorite is Bohren and Hoffman. This is a really excellent book um, to go much deeper into the concepts. So let us first discuss about history of Raman spectroscopy and life of Raman. All of you are aware of the origin of Science Day on 28th of February, which is related to Professor C.V. Raman's discovery of Raman effect. But the history goes to the prediction of inelastic light scattering goes to 1923. So it was predicted first by Smeckel that photons light can get inelastically scattered. Of course, concept of photons was involved. Um, uh, Okay, so and then quantum physics was still evolving at that stage. So then in 28, Raman and Krishnan they saw a very feeble fluorescence from neat solvents, and then Professor Raman wrote a paper in Nature, and based on that, after 2 years, he got the Nobel Prize in Physics. But the utility of this technique was limited because um, there were not many good sources at that time, not very powerful sources. So, uh, so people were not very excited about its applications. So, yes, physicists were looking at different systems, and the real excitement came when lasers came to the market. So laser having a very strong source and um, monochromatic source, and also you can have a linearly polarized light, and then you can get S or plane polarized light. So that made a lot of difference in the popularization of this technique. So people say that it was like chemists adopted physics, the child of physicists actually. So chemists uh, did a lot of new discoveries using Raman instrumentation, and finally the electrochemist actually uh, from one UK university they saw surface enhanced Raman scattering effect in 1977. So they were actually looking at some silver electrodes in a electrochemical cell, and then they found huge several order of magnitude enhancement in the Raman signals. So that was um, attributed to the rough metallic surfaces. I will speak about it. And then finally, in 1997, single molecule search was also possible. So this is a brief history. Of course, this technique has become more and more popular, and there are many other derivatives of these techniques, which I will not be able to speak in this lecture. For example, hyper Raman is there, and and then TERS is there, tip enhanced Raman scattering. Um, so this is brief introduction of the about the first person who spoke about possibility of inelastic scattering of light, Adolf Smeckel. And then finally, original experiment was done at Indian Institute of Cultivation of Science, and it was privately funded. So in this experiment, Professor Raman used um, uh, mercury lamp and benzene and direct vision pocket spectroscope. I think first experiment he used sunlight, I think, as far as I'm not wrong. And this is the photograph which I took at IACS Kolkata. And if you notice, in the building, main building, they have kept this original spectrophotometer, um, built by Raman in a glass cabinet. So this was actually the paper published by Professor Raman. The title is very short and sweet. A new type of secondary radiation. If you have interest, you can read this, download this paper and read it. So where did Professor Raman get this idea? He got this idea by challenging Rayleigh's theory on the blue color of ocean water, and also slightly bluish tinge in the glaciers actually. So people used to Lord Rayleigh actually gave a beautiful explanation about the blue color of sky, which we all know that it is because of the Rayleigh scattering, and which is scattering cross section is inversely proportional to lambda to the power 4. And people till that time thought that bluish color of ocean water is because of the refraction of the sky. But Raman had other thought actually. He said that no, it is because of slight shift actually in the due to water molecules when light strikes and interacts with the so there is inelastic scattering is involved. We know that Rayleigh scattering is elastic scattering. So then he proved his ideas, and so Raman effect is very similar. You can see that. So you have sunlight, and then you have, for example, when you put a violet filter, so and you have violet light, and then if you put some molecules here and let the light interact, so then you will find that it is shifted actually towards the low energy side as well as towards the high energy side, Stokes shift and anti-Stokes shift, vice versa, respectively. And then you can apply the filter, which we actually do in our system. We apply edge or notch filter, and then you can look at selectively one of those inelastically scattered light. So this is the first Raman spectra photographed in 1928. So it was taken on photographic films. These days, these photographic films are replaced by CCD arrays, charge coupled devices. So there also again we split that CCD chip into pixels, and more or less actually rather than imaging collecting those photons on a photographic film, we are collecting them in a pixel similar to your mobile phone. So still we speak that way, we actually get image, and from image we get the peaks actually. So Raman effect became the adopted child of chemistry because physicists were not very interested at the beginning, because obviously the source problem, and we did not have very powerful spectrometers. We did not have good detectors. So physicists are, as all of you know, that we are purist. We love to go to the finer details, and that's how we look at the basics. So but Raman spectroscopy could no longer compete with infrared. That was a problem until another development in physics. So lasers, which was another development in physics, that revived interest in Raman spectroscopy, as I mentioned. So let's look at the classical theory, which was given by Smeckel. So here we look at the electric field of the electromagnetic wave, which interacts with the system under investigation. So we can ignore the magnetic part and take only the plane wave. E is equal to E0 cos, and this is the frequency nu0 of incoming light, right? So which is actually a laser in this case, for example, argon ion laser or something else. So now this is E0 is the vibrational amplitude. Now, if there is a diatomic molecule which is interacting with this electric vector of incoming electromagnetic wave, so we can think about simple induced dipole moment E, which will be alpha times E. So alpha is polarizability, we all know. Alpha is alpha times, then we can put this uh, expanded form of electric field. But now, if we expand alpha polarizability, so polarizability is, we can write the first order term and then second order term, third order term we are ignoring, but they become very relevant when laser power is high, and basically they higher harmonics we take into technique consideration to technique which is called hyper Raman, but here we are ignoring it. So here, nuclear displacement Q can be written as Q0 cost 2 pi nu m and T. Here, nu m actually is the vibrational frequency of the molecule. Now, when we multiply, so this is actually polarizability. This is the first order term, and this is actually the change in the polarizability. So polarizability is basically how you can stretch the electron cloud around the system. It can be a solid or it can be a liquid, but like in molecule or whatever. So polarizability, so this is a change in the polarizability. And so the polarizability is less, then the Raman signal is going to be the less. All of you know. If we put this equation for the polarizability alpha here, this equation into this this is the first equation, and this is the second equation. If we put alpha, expanded form of alpha, then we get this uh, uh, this form, and then finally we can break it out into these three terms. So first term here, if you notice, it has this cosine function, and then but the frequency is nu zero. So frequency remains same here as it is for the incoming light. So this is called actually the Rayleigh term. And now if we look at the next term here, frequency has some addition by nu m, and this is there is another term. There is subtraction here. So this is Stokes, and this is anti-Stokes line actually, right? So first term is Rayleigh, and second term is anti-Stokes, and third term is your. So it is displayed here. So normally, if we have electric, so talk about electron going from valence band or HOMO in this case to LUMO, or valence band to conduction band, and then the excited electrons would like to come back after some time, and then it emits a relatively lower energy photon most of the time, but there are reverse cases also, which this effect is seen in phosphor materials, um, that you can get a photon of higher energy also, even in photoluminescence. So here you have, so basically Raman can be, Raman spectroscopy can principle by any, it's independent, it can be any frequency or any wavelength source can be used. The reason is that you don't need to excite the electron to the higher energy state. So here we see that virtual state. So electron get basically when the electron cloud interacts with the incoming photon. So so it goes to the so this is nu zero. Nu zero is the frequency of incoming light. So it goes to the virtual states actually. So then it comes back, and so then we call it like Stokes. This is Stokes, and this is anti-Stokes. So if the electron is in the um, higher energy, so this in the excited state, vibronic states, then if it comes back to the ground states, so then you have a higher energy, then it is anti-Stokes. But if you are able to tune the laser and in such a way that the laser energy is sufficient to excite the electrons all the way to the next electronic level, so then the scattering cross section is several order of magnitude higher. So that is called resonance Raman. But you have to deal with the problem of photoluminescence. So that I will discuss. Fluorescence will also be a part of the signal, and sometimes it can mask the Raman signals because Raman signal intensity is very, very weak. So here complete some, like, for example, for CCl4, 488 excitation. There is an example how typical um, Raman spectrum may look like. So you get Rayleigh signal very significant. So this is not to scale, but it is cut here because the intensity is too high in comparison to the feeble intensity of Raman. And if you notice that Stokes signal is here and anti-Stokes. So anti-Stokes, you can notice in comparison to the Stokes, the intensity is weaker. And that can be explained by the Maxwell-Boltzmann distribution law, because the population of molecule at ground state, Webernick state, is larger than the higher Webernick states. So that is the reason we get this kind of intensity effect. So resonance Raman effect, resonance Raman scattering is very useful to enhance the overall Raman intensity. And I have already explained that, but it is quite cumbersome because you have to find a laser which is the energy is higher than the band gap or homolumo gap, then only it becomes useful. Otherwise, it has really no use. So finally, you don't really present the anti-Stokes lines. So this is how you typically present the Raman shift, what we call it, X scale. And usually it is a convention that you basically plot it centimeter inwards. So this is how it is plotted. And you can plot it in electron volts or nanometer, but as a convention, as you can see that here, the same spectra is plotted in nanometers. But it is a convention that Raman shift is basically shift from the how much it is shifted from the Rayleigh line actually. And closer you go, basically toward this side, towards zero, and harder it gets, uh, uh, especially below 100 centimeter inwards. The experimentation becomes challenging. I will speak about it. So then you can assign several, all these peaks, and also it is possible to theoretically calculate using all these simulations, popular simulation, DFT, etc. You can find all these Raman bands, and that helps you to, for a simpler system, you can easily do that. Um, so in solids, we talk about phonon band, and then sorry, this phonon, EK diagram of phonon dispersion law, EK, and then we talk about all these acoustic modes and optical modes, longitudinal and translation mode. I'll not speak about it, but that's how we usually, as a physicist, we do. Probably you are already aware of it, the dispersion diagram. So acoustic modes, for acoustic modes, you know that at k is equal to 0, E is equal to 0, but it is not the same for the optical modes. Optical modes, k is equal to 0, is non-zero. And then yeah, but this is very important concept. The Raman and IR spectroscopy, when we talk about solid state physics, they allow only you to see only the photons closer to the zone center. Please remember that. Um, uh, in a typical dispersion curve. So if you look at the dispersion curve, this is how a complete dispersion curves looks like. So this is frequency, and if you notice. So you are looking at gamma point actually. If you look at gamma point, so you Raman So here, the reason is, so these are, so for example, it is for indium nitride. So this is frequency and it is 2 pi divided by lambda. You can, or you can write K, right? K and or an energy. This is E, and this is plotted as frequency centimeter inverse for your convenience, because that's how we relate centimeter inverse in a typical Raman spectra. So it is easy for us. So these are optical branches and these are acoustic branches. As I mentioned, that acoustic branches touches zero at when K is zero, the energy is this is zero, but it is not true for optical branches. So this is phonon dispersion curve, for example. This is zone centered. This is brilliance zone boundary, pi divided by A being the lattice constant. So this is zone boundary. So so wherever this curve basically meet K is equal to zero line, which is this line. So those uh, those Raman shifts only you record in a Raman or those vibrating states. So for example, you will see this point which is close to 100, let's say around 80, and you will also see something around 450. This you can see it here, 419 exactly. And so similarly, you can find points around 550 or more. Yes, 500. So these lines are somewhere here. So this is for gallium nitride. So these are slightly shifted. Yeah, and this is for indium nitride. But you do not get these values actually. The reason is the source. The source is actually we are taking visible light source mostly in Raman, and if we put wavelength here, so which is actually typically, let's say 500 nanometer, 600 nanometer. So this K value becomes almost close to zero. So you have to increase K. So if you want to increase K, you have to reduce wavelength. For example, you have to go to higher energy. So for example, if you want to explore these parts of the phonon dispersion curve, so then you would like to take tunable X-ray source. Then you can tune the energy, and then you can explore these sites of, you can go closer to the zone boundaries. But in a typical Raman spectroscopy, you do not go close to the, you remain close to the zone centered. So this is all described here. Um, so if you put typical lambda, so this becomes very small. It's almost close to zero actually. This is how it is described. And you can do, as I mentioned, you can do inelastic X-ray scattering, which is actually a new dimension of Raman spectroscopy. X-ray Raman is actually the new dimensions, new way of doing that. So tunable X-ray energy. If you can tune the energy of X-ray by taking different X-ray lines. So now let us discuss about the next important point, which is about the problem with the Raman intensity peaks, because there was a huge challenge earlier. So out of 10 billion photons, only typically one photon get Raman scattered, and that too, the scattering will be all around actually. It will not be like in forward direction, so it will be there will be angular distribution. So if you look at a typical solid cone, so where you detect, suppose for example your detector is placed here, and this is your sample, and here you have incident flux. So what will happen that towards your detector, so suppose this is the aperture of your detector. So if you draw a solid cone around the aperture, so depending upon the aperture, so you will be able to capture only few photons out of that. Please note that. So scattering cross section is very bad here. And one more thing we would like to note that the scattering cross section is inversely proportional to lambda to the power 4. This is frequency, or directly proportional to the frequency to the power 4. So it is this relation is similar to what we see in elastic scattering, that is Rayleigh scattering. And okay. So it's a this is beautiful slide which tells you a plot of cross section which is plotted at a logarithmic scale. And so if you note that here is uh, uh, so this is scattering cross section, and here we have SERRS, what we this is actually surface enhanced resonance Raman spectroscopy. So its scattering cross section is 10 to the power minus 15 somewhere here. You can see it here, and so this is quite high actually. This is quite high. And next comes SIRS, which we routinely do in our lab. We publish a lot of papers using virology, and so we have done a lot of work on this, SARS-CoV-2, the protein, spike protein of different all these four variants, and then we were able to look at the genetic differences in different strains using this technique. And also we looked at four different strains of dengue virus, and we looked at the antigen, actually non-structured proteins of dengue virus also, and we got very good signal here. Normally proteins don't give you good Raman signal because of the low electron density. Electron density is not very good in low Z elements. So, and now if you note that UV absorption spectroscopy is somewhere here, 10 to the power minus 18. And next comes fluorescence, which is quite close. But Raman is worse actually. Just pure Raman spectroscopy has a very bad scattering cross section. If you see, this is 10 to the power minus 29. And if you compare SIRS, which we routinely do, and this is basically, you can see that this is 10 to the power 13 difference, actually, huge difference actually, right? So Rayleigh scattering is somewhere here. It is also poor. So we have to really do something about it. So either you do resonance Raman scattering, which I mentioned, but resonance Raman scattering will have use photoluminescence background. So it is better to use SIRS. SIRS has actually e to the power 4 times enhancement. Yeah. So that's what it is described here, scattering cross sections for different excitation variable. So now first part is over, and let us go to the second part, which is Raman instrumentation. So there are four, we can divide the Raman instrumentation into four parts. First is basically the different kind of light sources, normally lasers. We don't use these days quartz tungsten lamp or something else. We solely use different kinds of laser depending upon the frequency, the energy which we are using, frequency. And then we have microscope, because we are looking at spot size, limited spot size. For example, we want to focus on a smaller area, so we focus it using a macro, that's called macro Raman. And you can, using microscope, you can do the raster scanning. Actually, you can pick up the Raman signal from different areas of the sample. And next is basically the spectrophotometer, because you have several Raman shifted photons, so you would like to split them and analyze them. So for that, you need a very good spectrophotometer. So there are two types of spectrophotometers. One is single monochromator based and triple monochromator based. I will speak about it. Then finally, detector is there, and then there are other optics. For example, you can use analyzer and polarizers. You can use scramblers. You can use you would like, for example, for manipulating the beam line, you would like to either you can use either lens systems or you can use mirrors actually. Some companies prefer mirrors over lenses because of the chromatic aberration which lenses give. So reflection-based systems are preferred uh, by some companies. Yeah, for example, Renishaw uses lens-based systems, and even uses uh, mirror-based systems. So this is the diagram, typical diagram. It can change from company to company, and sometimes these systems are highly modular, so you can design your own setup. You have a lot of flexibility. So here is laser, and then you have you have a linearly polarized light. So then this goes to the dielectric mirrors, and then another mirror. Then it may go to the focusing lens, um, because, for example, you would like to. So this is limited to the Rayleigh criteria, which we all know. Diffraction limited uh, resolution. Typically, it is half of the wavelength, right? Lambda by 2, or you can put it as 1.2 times lambda divided by n sine alpha. We know about Rayleigh criteria or Abbe criteria. So once you focus the laser on a small spot, for example, 1 micron area on the sample, then finally outgoing light will have a Rayleigh line as well as Raman shifted lines. Then so then you can put for example, you are doing polarization Raman spectroscopy. So uh, you can collect if you are if you are interested in polarization Raman spectroscopy, if you want to know the information about symmetry of the your crystal, then you can collect parallel and perpendicular intensities, right? And then you have a collecting lens, and then again focusing lens, and then you may use sometimes, depending upon the condition, scrambler. Then finally light goes inside the uh, slit, and then you have several monochromators here, uh, and then finally it goes to the either to the photomultiply tube or CCD these days. These days we don't use photomultiply tubes. I will probably share some slide uh, comparing the both, and then you get the data. So if we simplify the ray diagram, so we have this laser which um, interacts with the sample, and then we have to put this filter. I will speak about the limitations of this filter. So this is actually a Rayleigh filter. So uh, if you change the laser line, you have to change the filter type here. So there are two kinds of filters, notch filter and edge filter. So whatever your filter may be, the sole function of filter is to cut the Rayleigh. So it's so after that, once you get rid of Rayleigh line, so it's not like only the scattered, elastically scattered photons are cut, depending upon the quality of the filter. So there is some bandwidth. So you may lose some um, uh, you know lower phonon modes actually below 100 centimeter inwards. So there are solutions for that. Um, uh, Depending upon what kind of Raman shift you are interested in. Finally, we have a grating. There is actually a turret. Turret basically rotates, and it aligns the desired gratings depending upon what kind of a spectral resolution you are looking for. So grating actually decides your spectral resolution, how many lines per millimeter, and Then inside the spectrometer, there is a certain focal length distance between detectors. So this focal length is another very strong parameter which actually decides your spectral um, resolution. So larger focal length is always desirable. For example, typically um it is 800 millimeter in our setup, which we call HR 800 millimeter. So larger than 800 millimeter becomes too long and too cumbersome. But if you go to 2400 millimeter by making it round and round in okay, so more you spread out the resolution becomes better. So typical resolution is 1 centimeter inverse, but it can be better than that. It can be 10 times better. It can be 0.1 centimeter inverse. So finally, you have a detector, and so these are all the details: rejection filter and spectrophotometer and detector. Um, so as we were discussing, the role of filter is to reject the relay, to absorb the relay or whatever you call it, and allow Stokes and anti-Stokes lines and or whatever you are looking for. So edge filter actually stops anti-Stokes line, but notch filter allows if you want to record Stokes and anti-Stokes lines. So notch filter allows both, only blocks the relay line. Yeah, but there are advantages and disadvantages of both. So it's a big challenge actually to remove elastically scattered light, because 99.9% of the collected light is essentially elastically scattered light. So it is actually a stray light you would like to uh, remove, which we have already discussed that 1 out of 10 billion photons is 10 million photons actually, sorry, is Raman scattered. So now you need the other second challenge is you need a very good resolving power. So for example, if you are recording a Raman Stokes shift of 100 centimeter inverse, so if you are using argon ion laser, so wavelength is 540.531 nanometer. So if we convert that into centimeters, it becomes this value. So uh, so if we deduct 100 uh, from this value, so this becomes the wavelength becomes 517. So 17. So you are basically so this is the wavelength of incoming laser, and this you want to record. So and so you are very close to so suppose you put a filter, so it should have a very less uh, bandwidth, because you don't want to block this. And so that's the reason, if your filter is bad, so um, you are blocking this, also you are blocking this, because it get too close. But people record generally 10 centimeter inverse also. You can see that 10 centimeter inverse is very close to the source energy. So it gets really challenging and expensive to uh, use that kind of high-end optics. So generally, you can use um, all kinds of things. You can use UV, deep UV, you can use visible, you can use IR. There are advantages and disadvantages. So as the laser wavelength gets shorter, so your Raman scattering efficiency increases. Please remember 1 over lambda to the power 4 rule. So it really gets better, but risk of fluorescence increases. And sample damage may also increase. The cost of spectrophotometer also increases. So you can see that fluorescence signal can sometimes mask feeble Raman scattering actually. So these are some typical lines which people will use in ultraviolet. These are the choices sometimes. Visible, these are the choices. And so people uh, see what is affordable, and they buy those sources. And what source you would like to use, that depends upon the system which you are using and the type of Raman you are interested. For example, you are interested in resonance Raman, so you would like to see the Homolumo gap or band gap in your system under investigation. And based on that, you would like to select the laser. So here it is shown that scattering efficiency obviously drops drastically when you increase the excitation wavelength. So this is actually logarithmic scale. So it is really a very sharp drop. So while you move from, for example, argon to diode laser, this 785 diode laser or ND arc laser, you can see that you are compromising the Raman intensity multiple times, but you will get Raman shift is independent of Raman shift values in central universe is independent of the source. Only intensity changes actually. So this is fine. And now I'll move to the. So there are these. You will get these slides. You can read. There is not much for me to explain. So here we talk about advantages and disadvantages of various sources. For example, here we are talking about advantages and disadvantages of NIR lasers. NIR again has a lot of advantages in life sciences, where if you're looking at some tissues and cellular systems, so there is a biological window. So NIR can penetrate much deeper. And NIR has another advantage that you normally don't get fluorescence problem. But only disadvantage is that you obviously the scattering cross section becomes becomes quite problematic. So now the most important part is most expensive part is the spectrophotometer. So there are two kinds of spectrophotometer. One is basically Sherji-Turner and Michelson interval you are already aware of. Here you have a moving mirror, and then based on that you can look at different lambdas. But we use mostly dispersive kind of spectrophotometer where you have aperture and this inelastically scattered light enters here. Then one can have a mirror, and then you have a grating, and then using grating you split, and then you record it by CCD. It's a very simple system. Um, yes, so this is also described here. This is a mirror-based system. You see there are no lenses, mirrors, and but you can also have a lens-based system here. So using lenses also you can do the focusing and defocusing, but you have the problem of aberration, chromatic aberration, because lenses will have different focal lengths for different lambdas. So this is a very important slide. Here, if you look at this is actually the source part where you can have a polarizer, etc. This is actually the focusing optics. Your sample sits here, and this is basically microscope. So here you decide how much area you would like to expose, whether you can select 50x or 10x optics, and then Raman scattered light actually goes return to the same path, and then it enters into this red circle. And now this is called actually double pre-monochromator, and this can be entirely replaced by relay filter. So this is actually doing the job of relay filter, but it is much better than the relay filter, because if you use this monochromator instead of a filter, so here you can go much closer to the relay line. You can go to the low phonon modes, extremely low phonon modes, because you're using very high quality gratings here. So you are dispersing. So there are two kinds of double these monochromators. One is uh, uh, one is additive and another is subtractive. Actually, this one is subtractive. So basically, you disperse the disperse the light, and then you physically actually you can block the relay once you disperse, and then you merge them again, right? Mix them again, and then mix light because the relay is already you got rid of relay already. So the second grating actually you using part of the system. So then light enters into the final spectrometer. So essentially, this is not a triple monochromator. So this is actually a single monochromator only, but double monochromator plus this one more. So that's why it is triple, 2 plus 1. So this its job is actually to cancel out the relay, and it does this job much better than a filter can do. So you really go very close to the relay line. You can record even 4 centimeter inwards, 5 centimeters, which is impossible for a typical edge filter. And then this is simple. So this is called subtractive. If you use additive one, so for example, rather than merging the signal again using second grating, you can disperse it. And then even the resolution of the spectrophotometer becomes better. So instead of 1 centimeter inwards, which will be the case for subtractive triple monochromator, so you can get in an additive spectrophotometer, you can get resolution down to 0.1 centimeter inverse. This is really amazing. So I will show some examples. So this is so generally you get huge background also. So you can this is typical Raman signal for sodium sulfate in 1 centimeter cuvette using 785 excitation laser, and then 50 milliwatt. So it should be, so the power should be as small as possible, because most of the time users end up damaging the sample most of the time actually, because so the power should be under control and the exposure time should be as small as possible. Actually 800 seconds is too big. Here you are using it in water, so it's fine. When it's less likely that you damage the molecules, because water will have its own heat capacity and heat transport capability, thermal transport capability. So the molecules may not heat that much. But if you are focusing on a solid substrate on a tiny area, so then many times there are irreversible damages to the system. So then, because of water and cuvette, etc., you have a lot of background. So it's better to remove the background. So in the softwares, there is a provision that you can do that. So already we were talking about these triple stage Raman systems. So here your so this system is basically triple one. So here because we are not using filters, so if you use any wavelength, so the same system can be used for any excited. If you use any other laser, same system can be used because we are using monochromator, we are not using filter. So that's the advantage, that you can use tunable wavelength filtering spectrometer with a triple monochromator instrument. That's actually the ultimate tool, but it is actually highly expensive. Even our institute does not have that, but it is highly desirable for physics. Physicists actually, it's better to have additive type triple spectrometer, not even subtractive type, because physicists normally look at much higher resolution Raman spectra. So it is possible to work in a double subtractive single spectrograph mode. The first two monochromators are used as an integral pair, just now we discussed in the previous diagram, which firstly disperse both the relay and Raman scattered light and physically block the relay and then recombine the light. So here we are not taking advantage of dispersibility because we are remerging them, but we are taking advantage that relay can be very nicely blocked, whatever may be the wavelength. That's a beautiful thing actually. Third spectrometer is now act in normal way, the way even single monochromator system work. So advantage is that laser filter is infinitely variable, so you can use any wavelength. No need to change the filter actually when you change the laser. So one instrument can work with any laser sources, right? In addition, filtering performance is excellent. You can go down to, as I mentioned, 4 to 5 centimeter inverts. However, such instrument does require some more expertise. And additive triple monochromators are even more complicated to work with and require more expertise actually. So this is photograph of the ultimate Raman machine with three triple monochromators. As I mentioned that there is additive one. Additive one can improve the spectral resolution down to 0.1 centimeter inverts, and but single spectrograph configuration, which most labs have, it's also very good because it's very fast. It can do very higher throughput Raman sampling. So if you are looking at very fast analysis central facility, then it is better to buy this one. For specialized labs, you can go for triple subtractive, or the best one is this one, right? Whatever these are the configurations, but then price goes up and complexity goes up. So if you look at what I was telling you, that if you look at this is Raman spectrum from silicon germanium superlative, and it's a beautiful thing. You can observe that here we are able to go below even 100 centimeter inverse. Normally, single monochromatic Raman with filters, notch filter or edge filter, do not really go in this region. This region is normally remain unexplored actually. So here you see that we are able to record these lines down to 4 centimeter inverts. This is beautiful. This is really something. But if you take additive mode, you have additional advantage. You can see that if you take triple subtractive mode, you can record to the lower wave numbers, but the resolution is not very good. Resolution is same as the normal Raman actually, this one single spectrum. But here, if you take additive one, you can see immediately you have the same system oxygen here. You can see that so many peaks, new peaks actually come. So this is actually convoluted peak, Raman peak of so many peaks. So you can get high resolution Raman peaks. So you can get a lot of subtle information here, which is not possible, right? These are all convoluted. So relay filters are two types. If you're not interested, if you don't have money, or if you don't have access to triple monochromatic system, so single monochromatic system with filters are fine. So there are two filters, edge filter and holographic notch filter actually. The purpose is same. For example, ideal edge filter will be blocking the higher energies. Here it is blocking, the transmittance is 0, and it allows, so this is your relay line, red one, which is actually same as your incoming laser, and then it allows the other part. But you can see that it is close to the very close to the your relay line. And in reality, this is not as sharp 90 degrees. So in reality, it is like this. This curve is like this actually. So edge filter actually blocks below certain wave numbers, which is this is the problem. That's why you go to the expensive systems. So notch filters. So you can see that here we don't have access to we don't have access to the we don't have access to the anti-Stokes line, because anti-Stokes lines are here and then they are also blocked. So if you are to record anti-Stokes and Stokes both, then you can use notch filter. So notch filter, if you can see that it blocks only the relay line, and it allows anti-Stokes and Stokes both. But it has larger bandwidth, so you can see this is the real cutoff response from a notch filter. So you can see that intensity is almost 0 till 100, and then only it starts increasing. So and then it becomes flat here. So if you're recording something here, then you're in a problem, right? You cannot record in this region Raman signal, right? You cannot record this region. That's a disadvantage with filters. Notch filters are even worse, so which cannot record even broader. They have got broader absorption window actually. So finally, the detectors. There are two kinds of detectors: photomultiplier tubes and CCD camera. I will not speak much about it because I have to move to the next topic. But there is only one or two slides, I guess. So here you can see the comparison between PMT. PMT is actually single channel and CCDs are multi-channel. So that means you can record multiple wavelengths simultaneously. Here you have to record one by one and it takes long time. In this case, 20 minutes. And signal to noise ratio is very poor. It is 28 and signal to noise ratio here is, you can see it is an order of magnitude higher, 288 when you are, and recording time has really come down. So normally we use CCD or indium gallium arsenide based detectors. So spectrometer focal length plays a major role. So larger the focal distance, better the resolution becomes. For example, if you take 200 millimeter focal length, so the resolution dispersion will be you know not good in comparison to 800 millimeter, which will have higher dispersion. So the example is simple. You can look at the projector, your own projector actually, and if you when you put the screen far away from projector, so the obviously the objects look much bigger. If you keep the screen closer to the projector, then objects look smaller actually. So this is explained here. So if you bring this closer, so dispersion becomes poorer actually, right? So it is described here. So this is grating, for example, 1200 millimeter inwards. And so if the focal length, if you increase the focal length here, for example, here, so you can see the dispersion has gone up. So obviously you can resolve them better. You can see the distance between peaks is much better. And also if you change the grating, for example, so second thing which decides the resolution is grating type. So suppose if you compare between 1200 lines per millimeter and 2400 lines per millimeter, so you can keep the focal distance same in both the cases. But here for lasers, sorry, grating with higher rules per millimeter, the resolution is far better. So these are the two parameters which you can play, and you can improve but there is always a limitation. And obviously laser wavelength plays also a role, and detector also plays a role. I'll not go to the detector part, but you can look at uh, this table, which shows a summary of if you are changing actually grating type and lambda here, and how this band pass per pixel changes. It's beautiful data. I think you can correlate with which from this table what I just explained. Finally, you can compare between spectrum of CCl4 measured using a Raman, which has a smaller focal distance, 300 millimeter, in comparison to the larger focal distance, 800. You can see the same peaks look better resolved actually. So you are, otherwise deconvolution can be painful actually. So this was a final slide. Now I will speak quickly the third part, which are actually Raman-based technique, um, uh, spatial techniques. So this is the list of 16 techniques which are available, maybe more. Some of them are highly useful. For example, we have used this Raman optical activity in our lab, and we have used tip enhanced Raman spectroscopy is also very powerful. And we'll use Hyper Raman. I mentioned about Hyper Raman. You can use optical tweezer based Raman. You can trap the system using optical tweezers. angle resolved Raman spectroscopy can be done. And but I'll spend some time here and probably here. So you can so all these Raman techniques are based on static. These are all static Raman. So you are looking at you're collecting data in a very large in comparison to the atomic transitions. Your time window is very large, so it gives you averaged out information actually. So if you are interested in time snapshot, then you should do time resolved Raman. There people use pulsed laser actually, right? So if you use high, very ultra fast pulse lasers, depending upon how fast it is, you can capture different processes in. It's like one frame of entire movie. So polarized Raman, I already spoke that you can split the signal because laser is already linearly polarized. So if you look at polarization details, parallel and perpendicular, if you then you get a lot of information between parallel and perpendicular, and you can compare the intensity. This is rho here. This is cyclohexane is a very good example. So this is Raman spectrum for cyclohexane, parallel versus perpendicular. And here nothing you do actually you do this polarized and Raman spectroscopy very easily using conventional system. Only thing you polarizer and analyzer. That's it, nothing else. So once you split these energies, you can look at the depolarization ratio, rho, which is ratio of I intensity perpendicular direction and then parallel, right? And then you can learn a lot about molecular orientation, symmetry of bond vibrations, and many other things actually. So you can conclude about symmetry of symmetric or a non-symmetric nature of the system by looking at the depolarization ratio. Now I come to the next topic, which is surface transformer scattering. Here what we do actually, we take rough metallic surfaces with the nanometric roughnesses. And when we excite laser, actually what happens that surface plasmons are excited in this rough, nanometric rough surfaces. And when the molecule or your system, solid system, whatever system comes closer to these rough surfaces, then the electric field in the vicinity of these rough edges is highly enhanced. And because of the enhanced electric field, the Raman signal get enhanced, and that's we call as SARS. So normally people take silver or gold or sometimes aluminum systems with different custom-made substrates. So the pointed edges are much more beneficial. Like for example, star shape. So resonance frequency will depend upon the dimensions of the roughest dimension, and also shape of the these rough edges. For example, spheres will have only one peak, and if you have take rod shaped two-dimensional system, so then you can have two peaks, and then for prismatic systems, you may have three resonance peaks. So once you align the laser frequency with the surface plasmon resonance frequency, then you see the maximum enhancement in the source. And it is very powerful technique you saw from the table earlier that the scattering cross section, Raman scattering cross section is many times higher than on any other Raman techniques actually. So this is what we do in our lab, and we have published several papers, highly cited papers using this technique, using for various systems. For the lack of time, I may not be able to show. So this was first seen in 1974. This paper got published from pyridine molecules adsorbed at silver electrodes. So they saw anomalous increase in the Raman intensities. It also matters actually. I will not go into detail, but at NCL I teach in detail that depending upon how the molecule is sitting. So this is, for example, pyridine sitting like, so there can be like this hydrogen bond here how this nitrogen moiety is interacting directly with the silver electrode. Here in this case, for example, nitrogen is directly interacting with the silver moiety, or here you have water molecules. So your Raman signal of pyridine will be very different actually, and uh, you can actually say a lot about orientation of the molecule also. So this is beautiful technique actually if you go into detail. So there are two mechanisms. One is electromagnetic field enhancement, one other is chemical enhancement. You will read more details in the slides, but I can quickly tell you that chemical enhancement happens when this molecule is directly touching there is a chemical bond between the molecule which is under investigation, here in this case of pyridine, and the substrate actually. So for that electron transfer, electron sharing or something has to happen actually. The chemical bond should be there. So the electron cloud overlap has to happen between substrate and the system actually. If it is not there, then the chemical enhancement will not be there. But for electromagnetic enhancement, this molecule can be slightly away from the substrate, but not more than 10 nanometer, because electromagnetic enhancement the field enhancement get killed after few nanometers. So this is the difference between both. So chemical enhanced mechanism works at a very short range. No reference requirement, so you don't need to have rough surfaces. And here enhancement factor is 10 to the power 2 to 10 to the power 4, not much. So here charge transfer complex mechanism works here in this case. But in electromagnetic enhancement, you need to have a lot more, but there are rewards for this technique, because here enhancement is much higher, and so here you have to excite surface plasmons. So you need to take rough surfaces, and enhancement is greatest when plasmon resonance frequency is resonating with the radiation, but it does not mean that for other laser excitations there won't be much signal. You can still see limited enhancement actually. Uh, uh, so there are several ways to make substrates. So this is actually long range. For example, 2 nanometer, 4 nanometer, your molecule can be slightly away from the substrate, but still you will see. And the enhancement is quite large actually here. So this is how it works. So incoming electric field will excite the electron cloud, and then and put it into the oscillation. This oscillating electron cloud then start emitting also, and there will be enhancement. And so that's the reason that the Raman peaks get multiplied, and you can do a lot of use this very powerful technique actually. So there are many advantages. For example, fluorescence quenching will also be there because there are metallic substrates. So here you can see from one old paper that amino acid peaks are given, which is very difficult to measure on amino acids with silver colloids. You can see thymine, cytosine, and other things. So resonance Raman we already learned, so I'll skip it. So tip enhanced Raman is when you combine the power of atomic force microscope, which is another my area, with Raman, then you can do that. So here actually what you do, you come with the STM tip or AFM tip, and you have basically metallic tip. So and then you come to the your Raman sample which you want to investigate. Then basically you are exciting locally those molecules. So locally you are enhancing the signal. So what you can do, you can get the signal from few molecules, or for example, you are looking for Raman signal from one particle of, for example, let's say 50 nanometer. So this gives you for still a bulk measurement, even if it is if you collect from you use micro Raman, still you get many contribution from many particles or several millions of molecules. So so this tip enhanced Raman basically is used when you enhance very locally the area which you need. So suppose you have some material on a substrate. So so what you can do, you can take, you can image it using your AFM, and once you identify the area, then you can shine the laser, and then you can collect the Stokes shift. For example, here you can see that uh, you can record, you can start decreasing the number of molecules. For example, here you can see less than 5 molecules, you can still record Raman spectra. So this is the beauty. Actually, you can go down to the single molecule scattering. Thank you very much. This ends my Raman spectroscopy lecture, and then I hope you enjoyed. Send me any queries if you have. Uh, uh, Thank you very much.